This video is part of a course on food physics, of which this belongs to the application section. It is the first part of a four-part series on puffing. In this video, we will get an overall physical description of puffing in the context of rice puffing. The immediate follow-up video is going to look at the details of how temperature, moisture, pressure, all those variables vary within the little rice grain during the puffing process. As I said, this is the first video of this series of 4. We will talk about the overall physics of puffing. It's the framework for understanding the physics of puffing. As an example of puffing, here we see unpuffed rice on your left and puffed rice on your right. As we get started, to prime our thinking, some questions are worth pondering. Like, why does the volume increase? Is it just we heat up something and like most things expand, heated, the rice just expands? Is it just that? Or is it more? Or is there a sequence of events? What is the sequence of physics that could be happening? Now, another question could be, does water have anything to do with it? Of course, rice has only a small amount of water, but does the water have anything to do with it? And then does it puff the same whether we puff it at a lower temperature or at a higher temperature? Then is this puffing just for rice and maybe rice and other grains? Or it's a more general phenomena that could be happening in many different processes. So I would like you to pause the video at this point and think about these answers before you watch the rest. Here we have the big picture or the overall description of puffing. So we can think of a rice grain. This is from experimental results. A rice grain initially at 15% moisture is exposed to some high temperature at 200 degrees centigrade, and how puffing proceeds with time. And you can see where the puffing get started, and you can see the fully puffed rice grain. Below is an animation from the simulation of the physics that we are about to describe, about to build up. So here you see it gets heated, and here the temperature increases starting from the corner, and as the temperature increases, the material becomes softer, so the bulk modulus decreases. Also, as the temperature increases, we have evaporation happening, and that generates the pressure. In a second I will show. Here you can see pressures developing, and that pressure now pushes this softer material, so material having a lower modulus. So that is the overall description of puffing. Now we'll look into more of the detailed physics. Here you see a rice grain, and like many other food materials, we can think of the rice grain as a porous material, a porous medium. And if we really do detailed scan, you can actually see the porous structure like shown on the right. So we're going to consider this rice grain as a porous medium and then look at what physics happens during heat. So using a cartoon of this porous medium that the rice grain is being treated as, we want to talk about how vapor transports inside the rice grain. So the vapor can move through the pores by molecular diffusion through air in the pores. And then vapor can also flow due to gas pressure, like shown here in cartoon. So if we have a pressure gradient, that will cause the flow. So it can flow or transport by molecular diffusion through the pores. In the same pores, liquid water transports by capillarity. So here is a cartoon of that. Liquid water is transporting by capillarity, and capillarity can be shown to be diffusion like. So we can think of a capillary diffusivity for the water. But water can also flow due to gas pressure. So if we have high pressure and low pressure on one side and the other, then there can be flow due to gas pressure of the liquid. So the liquid can move by gas pressure and by capillarity. A portion of this rice grain is enlarged here. Now the rice has these phases like liquid water, vapor, and air. Each one of these phases would be moving through or transporting through the rice grain, driven by the driving forces mentioned in the previous two slides. For example, water would move by capillarity and gas pressure, in this case for rice. And for each phase then we do a mass balance. So we say what's coming in minus what's going out plus what's generated equal to the change in storage. This leads to the mass conservation equation for each phase. Solving the mass conservation equation for each phase provides the amount of water, vapor, or air at any location inside the rice grain and at any time. So we get the water amount, vapor amount, and instead of just the air, we combine vapor and air together, and that gives us the pressure equation. Now all of these details or the detailed derivations of the physics for these different phases and the equations and the porous medium details are in additional videos in a separate series on the theory part of this food physics set of videos. Just like the mass conservation for phases like water would give the amount of water at any point inside the rice grain as a porous medium, if we want temperature at any point, then we need to do energy conservation for this rice grain. Now the thing is, because of all those multiple phases, liquid water, water vapor, air, and then their individual driving forces like capillarity, or in case of gas, let's say molecular diffusion or flow. So multiple phases and multiple driving forces can make the heat transfer a bit complex. However, if we break it down to all of those phases and their driving forces, it's not bad at all. So let's go through the details here. So first, we think of heat conduction. So heat conduction, of course, happens through the solid, the water phase, vapor phase, and air phase. So we include this as a volume averaged thermal conductivity. Now the transporting fluid also carries energy. So let's look at the fluid phases: water, vapor, and air. And then each one can move due to capillarity or the pressure driven. Likewise for vapor, diffusion or pressure driven. So we just need to make sure that the contributions of each one of these phases is included in the transporting part, the velocity, whether it's due to a capillarity or due to pressure driven flow. For all of the phases need to be included. Evaporation, for example, would be taking away latent heat, and it is volumetric, meaning that it is distributed throughout. So that needs to be considered. And then finally, because of energy coming in and going out by all of these different modes, is going to lead to change in temperature, which has to do with the storage of energy inside this control volume. And so for the storage, which is this density times specific heat, that is going to be weighted by the mass fraction of solid, water, vapor, and air. By doing this, we are able to include all of the complexities of the different phases and the different transport mechanisms in a very mechanistic way, and we are able to include that in trying to calculate how the temperature changes. So the physics includes all of these detailed mechanisms. So all that discussion was about what's going on inside, but what's happening at the boundary, how it relates to the surrounding, is also going to matter. And so here we're now going to look at the boundary conditions, or what is happening at the boundary of this porous medium containing solid, liquid, water vapor, and air. So we focus on the interface. So we focus on this interface here, on the interface of the food and the outside medium. Since we have the mass conservation equation for water, vapor, and air, we are going to need boundary conditions for them. Internal water is transported to the boundary by two mechanisms: capillary diffusion or pressure-driven flow. Outside, there can be several possibilities. First is whatever comes to the surface, it just evaporates, and the evaporated part is removed, like using a mass transfer coefficient. The other part would be that so much of the water comes to the surface that it cannot evaporate and it starts to accumulate. So this is unlikely in case of rice puffing. Another possibility would be the flow part. If the boundary is already saturated and there is no place to hold more liquid water, if there's still pressure driven flow, it will just blow out when the boundary is saturated and you still have a pressure gradient forming flow. So this is also very unlikely in case of rice puffing. So most likely the situation at the boundary is that water kind of barely reaches outside, it's non-blowing, and then it evaporates, and that evaporated vapor is removed like in any diffusive mass transfer at a surface using a mass transfer coefficient. In other words, most of the transport of water outside is going to be after it evaporates and it being convected away. Likewise, for vapor, it reaches the surface by molecular diffusion and by flow, and then outside you have convective transport, just like we talked about this one after evaporation for liquid. And then for vapor, we also have the flow, which would be stuff being blown away. Now for air, as we said earlier, we don't use the air by itself, so we combine these two together to get the pressure equation. So for pressure equation, the boundary condition on the surface is simply P atmosphere, whatever is the surrounding pressure. So that completes the sort of the physics at the boundary. Now, all of that discussion that we had is about how liquid water moves and how vapor moves and air moves and also how energy moves. Now, the vapor and the air together, the generated vapor and air together, leads to pressure increase. And it is this gas pressure that really makes the rice to increase in volume. So these transport processes lead to the gas pressure gradient, higher pressure inside, lower ambient pressure outside. That leads to the deformation of the food matrix. That's really what causes the puffing. So the transport and deformation are what we call a coupled physics. Transport leads to the deformation, but as it puffs, it's more porous. So all of the transport processes, how heat moves, how liquid moves, or how the vapor moves, they all get changed because the porosity and permeability, those quantities all change. So deformation also affects the transport. So it's what we call a two-way coupling. Transport affects deformation, and then deformation affects transport. Now, the deformation itself is described by the equations of poromechanics, which I will share in the next slide. And the material aspect also comes into the picture, treating the rice as what we call a hyperelastic material. And then when it's melted, at high temperature, when the rice grain is melted, then it's perfectly plastic. So that's what we will talk in the next slide. And these other physics we have already discussed for the transport processes. The important point is they are coupled both ways. Now we're going to go very quickly through the physics of deformation in a very condensed way. The details of these, including all the equations and so on, are in the theory section of this food physics course, and it's a separate module on deformation in the porous media section. So anyone interested in more of the details can look into that module. So we think of the rice grain as a porous medium, and in that there are liquid and solids. They have their own pressures. Like we see in this cartoon for porous media, we have water and gas, and so they have their own pressures, and then there is the solid matrix. So think about it. If the gas inside, there's more gas generated, it's going to create pressures, and those pressures are going to be felt by the solid skeleton. So the equation of equilibrium goes something like this, that the total applied stress on this solid as a whole is shared between the stress on the solid skeleton. So the total on sort of the entire food, the entire rice grain, is shared between the stress on the solid skeleton here and the average fluid pressure. So fluid pressure is pressure felt by water and gas. Now, if we write the equations of equilibrium, then it's going to look like this. The total applied stress is 0 because the rice is not being pressed, or there's no force on the rice. There's no external force on the rice. So if we write the equation for equilibrium, then it becomes 0 equal to the effective stress on the solid skeleton plus the average fluid pressure. Because the applied stress is 0, there's nothing external, then these two guys balance each other. So this makes kind of sense, that the evaporation and this gas pressure that is developed inside is balanced by the stress that is developed in the solid skeleton. These two balance each other because the rice as a whole is not jumping around, or there is no external force that is acting on it. Another driving force for the volume change can be water loss, or the shrinkage due to the loss of water, but that part is being ignored for now. So then we can find the stress if we know the fluid pressures, and the fluid pressures we know because we know how much evaporation is happening and how much of that vapor is leaving. All of that in the transport equation earlier is going to give us the fluid pressures. If we know the gas pressure and if we know the liquid pressure, we can take an average of them, a weighted average, to get the fluid pressure. And the point is, we know the fluid pressure, and because we know the fluid pressure, we can find the stress on the solid skeleton. But if we know the stress, then we have to know how much is the strain, or because of the stress, how much does it deform. So what we need is material models on how the rice deforms. So here the rice is treated as hyperelastic and followed by plastic, and there is this huge effect of temperature, as you can see. So the elastic modulus, for example, when it is hard and glassy, it is much higher, and as it's heated, it goes soft and rubbery. So it goes through these huge changes in modulus that would need to be considered. You see that that's a very, very critical part of this rice puffing process and how far it's going to puff. But once it's completely melted, then it's treated as like a plastic material, and so it will have its yield stress, and the yield stress is also changing with temperature that is included in the material model. So the material behaves like a hard and glassy at the lower temperature, and then it becomes soft and rubbery. All of that transition would be included, and it will vary from one location to another depending on the temperature at that location. And so we're talking about the material being very non-uniform during the puffing process, spatially speaking. Now, it is absolutely not our purpose to get into the details of the equations. That is the reason I did not show equations in the previous slides. So this one is just a very, very quick snapshot of the equations. So then we have the three mass balance equations. This one is for water, and then this one is for vapor, and this one is for vapor and air, that is the gas. All of them have this flux term, and the flux for water, let's say, for water, the flux has three terms. One is the convective part, that is due to pressure driven flow. One is capillarity or diffusive like, and there is a third term that has to do with the matrix deforming. So if the matrix itself is deforming, we need to kind of bring in the velocity of the solid matrix. That's what gives the third term. So you notice that these fluxes are written with respect to ground. Moving on, the evaporation term, the rate of evaporation that shows up in water as a -1 and for vapor as a +1. The water evaporation has an equation like this, and then here is the energy equation. So remember all those phases, each one of them transports energy. That's why it's a summation over water, vapor, and air. And finally, here are the mechanics equations. So remember I was saying that the pressure, the fluid pressure drives the stress in the solid. That's this equation. Now that is rewritten into different forms of stress and so on. That leads to this one, leads to this one. But most important part is this pressure in the fluid drives the stress. So the thing to remember is, if you're interested in these equations, then in this specific case of rice puffing, you can go back to the original publication. Now, since I showed you all the equations, I should spend a few seconds at least to talk about how the equations are solved and also what other physics is included. For example, the properties. Okay, so the properties like permeability, how liquid moves through the porous matrix, they vary with porosity and saturation, which varies with position and with time. So those need to be included. Then capillary diffusivity varies with moisture and temperature, and that again varies from location to location. Then the mechanical properties vary with glass transition, as already mentioned, and then the yield stress values also vary. So with that, we spend a few seconds on solution details. So they are solved in a commercial software, COMSOL Multiphysics, which is a finite element based software. There can be other ways of solving those equations, and they become computing intensive. So 15 seconds of puffing took 64 hours of CPU time on a 12 core machine. Now, so next we will just look at the solutions that include all the physics that we discussed, the transport of water, and that's due to capillarity or pressure driven flow, and transport of vapor due to diffusion and pressure driven flow, and how all of those liquid and vapor carry the energy, and then vapor and air together build the pressure, and then the pressure inside causes the stress, and the stress combined with the material property, how the material behaves, the rice material behaves, gives us the strain or the deformation of the rice material. So that's how we know how much it changes dimension or how much it pops.